Yes, good morning to everyone. So my screen is visible.
Yes, sir.
Okay, then we will go for the lesson here. So today we will discuss about the diffusion and drift once again. Okay, so that also some important question. Okay, see here. So in this carrier generation and uh, recombination, so uh, generation, recombination, and carrier transport. So these combinedly one question. So carrier generation, so carrier recombination, and carrier transport. Okay. So already we know that what is the generation, carrier generation. So carrier generation means so generation of electron and hole pair, electron and hole pair. Who is that? One is unmuted. So mute yourself. Okay, here, so carrier generation and carrier concentration we are discussing here. So first of all, so carrier generation. Carrier generation means that means generation of electron and hole pair. When we will give supply to the supply energy to the valency band, what happen? So these electrons will be jumps from valency band to conduction band when we will supply the energy to the this valency band. So that energy is like electrical energy, thermal energy, or photon energy, whatever the energy it will be there. So that energy should be greater than the this energy gap. The supplied energies should be greater than the this energy gap. Then only that valency electron will goes from valency band to conduction band. At the time, what happen? So in conduction band, electron will be present, and in valency band hole will be present. So this is the electron hole pair generation. Electron hole pair generation. Okay. Now, so there is a generation rate will be there. So no need those are for you. Okay. So now recombination of electron hole pair. Okay. So recombination means this excited electron, or so that the electron will be in conduction band, so doesn't stay more time, okay. So that's why what happened after certain time it will comes to the that valence band electron comes to the conduction band electrons comes to the valency band after certain time, because so in conduction band electron does not stay much more time. Okay, so that's why what happened after certain time that electron comes to the valency band and recombine with the hole. In this process what happened? So some energy will be emitted. That emitted energy is in the form of photon or heat. Okay, depends on the but what is that jumping process. Okay, so here that energy released energy is so depends on their energy gap. Okay, so here also, so that whatever what happened, so here electron will jump from conduction band to valence band. In that particular process energy will be released. So that energy is depends on the that type of energy, which type of energy is released. Either it will be photon, or so in the form of heat, or so sometimes phonon also will generate. So that will be depends on the direct and indirect band gap. Direct and indirect band gap. We will discuss that direct and indirect band gap in next class. Okay, that means not on next class, next unit. Okay, so the direct band gap and indirect band gap we will discuss in next unit. Okay, so depends on that direct band gap, indirect band gap. So that what is that? This energy, released energy will be depends on either it will be photon or phonon or in the form of heat. Okay, so there are three ways. So that generated three ways of energy will be generated here. Okay, this is the recombination process. Now, so carrier transport. So in the so how carrier will be transport? That means so in the form of either diffusion and a drift process. In case of semiconductor, how carriers are nothing but either electrons or holes. either electrons or holes. So how they transport from one place to another place means, so there are two processes are there. So one is the diffusion process, another one is the drift process. Okay, if electron is moving like diffusion process means, so that current we will call it as diffusion current. Diffusion current. So if electron will be moving, so due to the drift process, so that current we will call it as drift current. So now we are calculating the diffusion current density and drift current density. Diffusion current density and drift current density. So first of all, so what is the diffusion? What is the diffusion and what is the drift? So first of all, we will discuss about the drift. So drift is nothing but, so generally if you will take any semiconducting material, so at a particular temperature, if you will take so more than room temperature means, so there are so many free electrons will be there in conduction band. So those free electrons will move inside the semiconductor, but in random motion. So without applying any external voltage or potential difference means what happens? So there is no flow of current, because so those carriers are will move randomly. So in different directions. That's why so there is no resultant current. In case of metals also same. Okay, so at without applying any external voltage, inside charge carriers will be there. Those carriers will move entire the material. But so those carriers will move in random motion without applying any external field. So after applying external field, so what happens means, so those either electrons or holes will move in a particular direction, depends on the potential difference. Yeah, I will explain you how it will be. See here, so that means if you apply the potential difference here, means, so all electrons will move in a particular direction, so that negative terminal to the positive terminal. Okay, because of so this motion of electrons, so current will be passing through the semiconductor. Okay, similarly, so due to the holes here, so holes will move from so positive terminal to negative terminal. So when it will move means, so particular direction means if you apply the potential difference or external voltage. Okay, so at that situation only it will move in a particular direction. Otherwise, so inside the semiconductor, so may those charge carriers will move, but so those will move in random direction. That's why there is no current flowing through the circuit. Okay, so now here if you observe that it will move particular direction, that's why there is a resultant current passing through this circuit. Okay, so here, so due to the external field, due to the external voltage, here current is passing. So that's why, so this current we will call it as drift current. If you apply the so voltage difference or potential difference or anything, so what happened? So due to that voltage, what happened? Current passing through the circuit. That current we will call it as drift current. Okay, so this is about the drift current here. So here, so these free electrons will move with a, if you apply the so particular voltage, what happens? Those free electrons will move with a particular velocity. That velocity is steady velocity. So that velocity we will call it as drift velocity. Drift velocity means all electrons will move with a particular velocity only. All electrons will move so with a particular. Suppose if you will observe the raindrops. So all raindrops coming with a constant velocity. So that means so all raindrops whenever touching to the ground, so it all have same constant velocity. Okay, so constant velocity if you will take at a particular time, like that here also all electrons have some steady velocity. This velocity we will call it as drift velocity of electrons. Okay, so due to this drift velocity, what happened? Current passing through the circuit. This current we will call it as drift current. Okay, yeah, see here definition is given. The drift current results due to the drifting of electrons under the influence of external voltage. Okay, this is the definition of so drift current. Okay, velocity. So what is the drift velocity? So the drift velocity of the electrons is proportional to the applied electric field. So electric field is nothing but there is a relation between potential and electric field, potential difference and electric field. Okay, so that's why we can call either pronounce electric field or potential also here. Okay, that's why. So V is the velocity. Velocity is proportional to the electric field E. Velocity is proportional to the velocity means here drift velocity. Drift velocity of the electrons is proportional to the electric field. Okay, there is a some proportionality constant. That proportionality constant V is equal to mu into E. So what is the mu? Mu is the mobility of charge carriers. Mobility of charge carriers. So it will be mobility is different for electrons as well as what is that holes. Okay, so that's why. So far, if you want to take electrons means we will take mu E. So if you want to take holes means so velocity of the holes. So V. So velocity of the holes V is equal to so mu H into E. Okay, so like that there is a two velocities, that is the one velocity for electron, so one velocity for holes. Okay, now here one more definition is given, mobility. So mobility definition. Okay, so already so mobility formula mu is equal to V by E. V by E. So from this formula so we can give some definition. So mobility is defined as the value of the drift velocity per unit electric field strength. Okay, so for unit electric field strength, so that is called as mobility. So once again, mobility is defined as the value of drift velocity per unit electric field strength. Okay, so that means if you will take mu is equal to V by E, if you will take E is equal to 1, E is equal to 1 means so mu equal to V. So that means if applied electric field will be so 1 unit electric field, 1 unit electric field. So then so drift velocity is equal to the mobility. Drift velocity is equal to the mobility. Okay, this is definition of the mobility. Now here, thus the faster the particle moves at a given electric field strength, the larger the mobility. If electron is, so that means mobility is different for different materials. Different for different materials. It also depends on the temperature. It also depends on the temperature. If you increase the temperature, so in case of semiconductors, so mobility may enhance. Okay, so that means that mobility is different for different materials. If mobility is more, means so that electron will move faster. Either electrons or holes will move faster. Okay, see here. Holes mobility is equal to V is equal to mu P into E. So mu P is the mobility of hole carriers. Similarly, so yeah. So here current. So current density. So the current density is due to the drift. So due to the drift of the electrons. So the current density drift of the holes here. Drift of the holes, that current density JH is equal to E into P into V. E into P into V. E is the charge of the hole and P is the charge number of charge carriers. Number of holes, how many holes will be present. Okay, so JH is equal to E into P into V is the velocity of the hole. Velocity of the hole. Okay, already we know that V formula. So velocity of the hole V is equal to mu into E. Mu into E. So therefore, current density. So drift current density of the holes is equal to so E into P into mu P into E. So this is the drift current density. Drift current density. Now coming to the electrons. So now coming to the electrons, J is equal to NeV. We know that formula, J equal to NeV. Already in Hall effect we discussed. So current density J is equal to N into N means number of electrons. Number of electrons. Okay. Into number of electrons or density of electrons we can take. So N into E is the charge of the electron into V. V is the velocity of the electron. Okay. So in place of V, if you substitute the so that formula, there is the relation between electric field and so velocity. So if you substitute that formula, so drift current, sorry, current density, drift current density of the electrons is equal to E into N into mu E into E. So this is about the drift due to the drift. So now total drift current is equal to, so due to the drift of the current density of the electrons plus current density of the holes. So current density of the electrons plus current density of the holes. So total drift is equal to. So this is about the drift current density. Drift current density. So in case of intrinsic semiconductor, here N equal to P. N equal to P is equal to Ni. Okay, intrinsic carrier concentration. So if you will take, so common means we can get the particular equation. Okay, this is about the drift. Now coming to the diffusion current. So diffusion is nothing but very simple. Suppose if you will take two gases, either any take one gas. So one gas means, so if you release the gas, what happens? So that will move from higher density to lower density. That gas will move from, so that means diffuse from higher density to lower density. That means gas is diffused from, depends on their density concentration. Density concentration. So if density concentration is high means, so that will move from low density concentration. So that gas will move from high density concentration to low density concentration. That means it depends on the density gradient. Density gradient. Density gradient is nothing but, so number of charge carriers by, so per unit length. Number of charge carriers per unit length is called as what is that? Dense. What is that? Yeah. So density here. Now here, see here. In semiconductor, in addition to drift current, there is another current is known as diffusion current. So this current results due to the phenomena called diffusion. Okay, diffusion mechanism is analogous to that which occurs in gas container where the gas density is not uniform. The gas particles move from higher density area to lower density area. Okay, like that. So electrons also will move from higher density area to lower density area. Similarly here in a semiconductor, the charge carriers flow from high doped area to lightly doped area in a non-uniformly doped semiconductor bar. This is called diffusion. Okay. So now if you will take semiconductor, pure semiconductor, suppose we are doping from only one side, means what happened? So only one type of doping we are adding here. So either p-type that means pentavalent and trivalent element. If you add the pentavalent element means, so that electrons will diffuse from higher concentration gradient to lower concentration gradient. Okay, lower concentration gradient. Okay, like that. So in the diffusion will be occurs up to equilibrium position, up to equilibrium position. Similarly holes, if you dope with the trivalent element from one side, what happens? So that holes will move from one side to another side. Holes will diffuse from one side to another side, from higher concentration to lower concentration. Okay, the current resulting from the movement of charge carriers due to diffusion mechanism is called as diffusion current. Okay, so see here, so that means here electrons will move from higher concentration to lower concentration. Similarly, holes will move from higher density concentration to lower density concentration. So due to this process, what happened? So electrons are moving one side to another side. Some current is passing through the circuit. Some current is passing through the circuit. So that's why, because those electrons will move from only one particular direction. So due to this current, due to this motion, some current is passing. That current we will call it as diffusion current. Diffusion current. Okay. Yeah. So let us consider a semiconductor of specimen cross-sectional area A whose concentration of charge carriers. Suppose if you will take p-type charge carriers, so varies with a distance dx. Charge carriers varies with a distance dx. Suppose if you will take one particular distance, charge carriers will density will be high. So if you will take another distance, so that charge carrier density will be less. Okay. So and establishes gradient in the specimen. Okay, so that means if you will take, that is dp by dx, dp by dx, that is the density gradient. density gradient dp by dx. Here we are taking holes, that's why so holes density varies with the length, varies with the length dx. Okay, so that means so dp by dx gives the density gradient, density gradient. Yeah, see here, if x increases, the current density decreases because hole concentration decreases, whole concentration decreases. Okay, so now this is the that current density, the current density is proportional to the, so these density gradient, density gradient dp by dx, density gradient dp by dx. So jp, if here we are taking for holes, that's why jp is proportional to dp by dx. Okay, so this is the jp is current density due to the holes. So current density due to the holes in the diffusion process. Diffusion process. Similarly, so this is Jp proportional to dP by dx. Here Jp is equal to minus E into dP into, so capital D suffix P into dP by dx. So here, so D, so D is the diffusion constant. Diffusion constant or diffusivity, diffusivity of a semiconducting material. So diffusion constant or diffusivity of the semiconducting material for holes. Okay, so this is the Jp is equal to minus E into dP by dx. So this diffusion coefficient we can calculate by using, here there is a Einstein relation will be there. Einstein relation will be there for calculating the diffusion constant. Diffusion constant. So that is not required for you. So Einstein constant for diffusion means you can get the, so suppose if you want to, that means you can search on the book also, book also it will be there, so that is not required for you. So by using that Einstein equation, so we can calculate the this diffusion constant value, this diffusion constant value for particular material, particular material. Okay, now J is equal to, so minus E into dP, so capital dP into, so dP by dx. This is the density of the holes. So density of the, current density of the holes. Okay, so current density of the holes. Now coming to the, so diffusion current density of electrons. Diffusion current density of electrons means same formula. Je is equal to, here there is no minus will come, no minus will come. Okay, so Je is equal to E into dn by dx, dn by dx. So that is the, so current density due to the, current density due to the electrons. So current density due to the electrons in diffusion process, diffusion process. If you observe the resultant, if you observe the resultant one means, see here, yeah, so that total diffusion current density J is equal to, so we can add both, we can add both E into D into, so dou n by dou x minus E into dh, here instead of P here taken H. Okay, so minus E dh into, so dou P by dou x. So this is the resultant diffusion current density, diffusion current density. So this is about the, so current density of the hole as well as current electrons. Okay, electrons. Okay, so in current density of diffusion and, so drift we are discussing here. Current density of diffusion and drift we are discussing here. So these are the some equations of, so current density of the due to diffusion, so diffusion as well as current density of the due to drift, due to drift. Okay, so now okay, how many are there here? 99 members. Okay, so this is about the, so transport of charge carriers, transport of charge carriers. So if they ask transport of charge carriers means you have to write the, so diffusion process as well as drift process. Okay, so drift process, this is about the so semiconductors topic. So now, so total topics are completed. So if you have any doubts means you can ask in this. So do you have any doubts on these topics? First of all, we will revise once again. So on each topic, so introduction is so not that much of necessary. So from which onwards we will discuss means, yeah. So this carrier concentration of intrinsic semiconductor, carrier concentration of. So mainly here, so what are the main asking questions means? So carrier concentration of intrinsic semiconductor. So that is the first question. So if they ask carrier concentration of intrinsic semiconductors means, you have to write the density of the holes as well as density of the electrons, density of the holes and density of the electrons. So you have to prove, so two. Okay, so if they ask particularly, so calculate the equation for density of electrons. In case of intrinsic semiconductor means, you can derive only density of the electrons, n value. Okay, so suppose if they ask carrier concentration means, you can calculate both, so density of holes and as well as density of electrons. That is the first question coming in the semiconductor materials. Second question is extrinsic semiconductors, carrier concentration of extrinsic semiconductors. So in carrier concentration of extrinsic semiconductors, so two will be there. So one is the N-type semiconductor, another one is the P-type semiconductor. Okay, so in N-type semiconductor, so what are the charge carrier concentration? We have to calculate. We have to calculate in P-type. So what are the carrier concentration? We have to calculate. So those are the two questions. And so sometimes they will ask, including that, so dependence of Fermi level with the temperature, as well as concentration of the doping. That means doping concentration. Doping concentration. So they will ask the so p-type semiconductor, extrinsic charge carriers in p-type semiconductors, so, or n-type semiconductor. They will ask along with that, so dependence of Fermi level with temperature as well as concentration, doping concentration. Okay, so that is the one more question. And the next one comes to the Hall effect. So Hall effect is the one important question. So they will ask the Hall effect of the semiconductor. So in particular, sometimes they will asking for electrons. Sometimes they will asking, so particularly for holes also. So for holes, how it will be depends on. So after deriving, so what you will write conclusion means, for holes RH value will be negative. For electrons RH value will be for electrons RH value will be negative. So for holes RH value will be positive. Okay, like that you have to write. So first of all, initially we have to take charge carriers. Okay, charge carriers means, so after proving the equation, so we can take RH for electrons, RH for holes. Like that you can write. Okay, so that is in case of Hall effect. Okay, next one. So this recombination and generation and recombination of charge carriers and transport of charge carriers. That is the one more question. So generation means, you can write the just definition and draw one diagram. So and same recombination means, so definition and you draw the diagram. And after that, transport of electrons means, you can write diffusion process and drift process. There are two types of transport mechanisms are there. So like that. So what are those means? So diffusion and drift. So first write the definition of diffusion, then write the definition of drift. After that, so write the diffusion current and drift current. Diffusion current density, drift current density. So that is for one question. And next, so PN junction diode. So write the characteristics of PN junction diode. IV characteristics of PN junction diode. That means, so you can write the PN junction diode. So and IV characteristics in forward bias and reverse bias. So by using energy level diagram, you can explain. So they will ask specifically by using energy level diagram. So explain the IV characteristics. Okay. So while drawing the what is that p-type forward bias and reverse bias. So for zero bias, how it will be energy level. For forward bias, how it will be energy level. So energy level diagram will be there. I explained you how it will be there. So after that, reverse bias, how energy level will be there. Okay, you have to discuss like that. That is in case of PN junction diode, they will ask the question. And Zener diode. So particularly So write the that means uh, discussion about the Zener diode and forward bias characteristics or reverse bias characteristics, and so particularly they will ask the applications and Zener breakdown also. Zener breakdown. Okay, so Zener breakdown. So those are the so important questions in this. Okay, some formulas. Sorry, some problems also they will ask. Some problems also they will ask. Okay, so we will discuss the problems also tomorrow. So in next class. Okay, so is there any doubts in this class? That means in this topic. So you did not understood any topic. That means we will discuss the topic on next class. So which topic you did not understood? Everything you understood? So I will send the material today. I will send the material today. So this PPT as well as PDF. PDF. Okay, in that PDF class notes will be there. So that class notes I will send. Okay, and this PDF will I will send. So compare both and so prepare notes yourself. Prepare notes yourself. So that notes is your assignment. That notes is your assignment. Okay, so already now I told some questions. That questions only, yeah, okay, assignment questions. Assignment questions. Okay, so prepare notes yourself. Okay, now so here just once we will discuss intrinsic semiconductor briefly here. So already we know the definition of intrinsic semiconductor. Intrinsic semiconductors is nothing but pure semiconductors. Pure semiconductors. So that Fermi level will be in between the valency band and conduction band. Okay, so this is so someday it will be there here some definition introduction. Yes, some introduction will be there here. Suppose if you will take germanium and silicon, so these are the fourth group elements. These fourth group elements are the best example for intrinsic semiconductors. Intrinsic semiconductors. So okay, if you will take silicon, so silicon have so it's here four valency electrons. Silicon have four valency electrons. Okay, so that those four valency electrons are bonding with the surrounding silicon. So these every silicon atom is so bonding with the surrounding silicon atoms. Surrounding silicon atoms. So here, so those electrons. Suppose here in this, suppose if you will take these two silicon atoms here. So one silicon atom supplies one electron. This silicon atom supply another electron. These two electrons are sharing both two silicon atoms. So this bonding we will call it as covalent bonding. Covalent bonding. So covalent bonding occur between surrounding all silicon atoms. Surrounding. So if you will take here, so one silicon atom, so covalent bond with surrounding four silicon atoms. Surrounding four silicon atoms. This process occurs throughout the crystal. Throughout the crystal. Okay. So this yeah, silicon and germanium. If you will take germanium also, same process will be there. Okay, so this shape of the shape will be tetrahedron shape. So if you will take each so each bonding of the one silicon atom will be tetrahedron. If you will take resultant means diamond cubic crystal structure. Diamond cubic so crystal structure. Here not displayed this one. Okay, yeah, I think it was missed. That diamond structure, cubic structure was missed here. Okay, so that is the diamond cubic structure. Resultant structure will be. So if you will take each, that means one silicon atom, it's one silicon atom is bonded with surrounding four silicon atoms. It form a tetrahedral structure. If you will take unit cell of the silicon, so that structure will be diamond cubic structure. Diamond cubic structure. Now carrier concentration of intrinsic semiconductor. Okay, now here when suitable form of energy is supplied to the semiconductor, then electrons take transition from valency band to conduction band. Hence, free electrons in conduction band and simultaneously free holes in valency band is formed. This phenomena is known as electron hole pair generation. In intrinsic semiconductor, the number of conduction or free electrons will be equal to the number of electron vacant site for hole in the valency band. Okay, if you will take intrinsic semiconductor, so the number of electrons in conduction band is equal to the number of holes in a valency band. Okay, see here. So how many number of electrons will be present? So that much of holes will be present in a valency band. Okay, so now their effective energy or kinetic energy of the electrons. If you will take here in conduction band, electrons will be present. So those effective energy or kinetic energy will be so EC is the what is the EC here? EC is the energy of the minimum energy of the conduction band, minimum energy level of the conduction band. Okay, so that minimum energy level of the conduction band. What is the maximum energy means? We don't know. We don't know.
Sir.
Yes, sir.
Go for full screen.
Yes, sir. Okay, see here. So this is the minimum energy of the conduction band, and the maximum energies we don't know. That's why we will take here maximum energy of the conduction band infinity. Infinity. If you will take effective energy of the electron, effective energy of the electron equal to so E minus EC. E minus EC. That effective energy are kinetic energy. So kinetic energy of the electron. Okay, kinetic energy of the electron equal to E minus EC. E minus EC. Okay, so this is the effective energy of the electron here. Similarly, effective energy of the hole. Effective energy of the hole here. So that what is the effective energy of the hole equal to? So see here, if you will take, so what is the maximum energy of the valency band? So EV is the maximum energy of the valency band. EV is the maximum energy of the valence band. We don't know what is the minimum energy of the valence band. So that's why what we are taking here, minimum energy of the valence band is minus infinite. Minus infinite. Maximum energy is the of the valence band is EV. Okay. Now you will take effective energy of the hole. Effective energy of the hole means so that hole will be present below the valence band. So below the valence band. If you want to take effective energy means EV minus E. E is the energy of the hole here. So energy of this particular place. If you will take effective energy means EV minus E. EV minus E. So that are also called as kinetic energy. Kinetic energy. Okay. So this is about the so how you will take so energy of the electron, energy of the hole. Okay, so yes, whatever the so that means why we are taking E minus EC means here so E is greater, E is the energy of the electron, so E is the greater than the EC. That's why we are taking here E minus EC. Similarly here also. So why we are taking EV here means so EV is the maximum. EV is the maximum and E is the minimum. That's why we are taking here so EV minus E. So in the equations also same we will take. Okay. So calculate the density of the electrons. Calculate the density of the electrons. So density of the electrons, let Dn be the number of electrons per unit volume. Dn be the number of electrons per unit volume at a particular energy level. So E and E plus DE. E and E plus DE. So now Dn is equal to. So Dn is equal to Dn is the density of the electron in a particular energy gap. Particular energy gap E and so E plus DE. So if you will take, so Dn is equal to, so what is the Dn, why we are taking it? Suppose here in this energy, suppose here energy is E. So if you will take DE, okay. So DE means, so from here level to this energy level to this energy level, how many electrons will be present? How many electrons will be present? So by using this equation, we will calculate. So in that energy level, energy gap, so in that energy E and E plus DE, in this energy range, so how many electrons will be present? Dn. Okay. So is equal to Z of E dE into F of E. F of E is the probability of finding the electron. Probability of finding the electron. Okay. Z of E dE is the density of states. Density of states in the okay, so each state how many electrons, so many electrons will be present here. Suppose here how many states will be the density of states, how many states per unit volume, that is the density of states. So in the energy range, so this is the energy E, so this is the energy E plus DE. In this energy range, how many energy states will be there? So that is the so Z of E dE, Z of E dE, that is the energy states. Okay, and F of E is the Fermi energy. So Fermi energy level. So Fermi equation. So by using this Fermi equation, we can calculate the probability of finding the electron in a, so that a density of states. Density of states. Okay, probability of finding the electrons in a density of states. So resultant. So Dn gives the Z of E. So total number of electrons in a particular energy range gives the Z of E dE into F of E. If you want total number of electrons, suppose if you will take this total conduction band, how many electrons will be present? How many electrons will be present means that is equal to N is equal to so integration of Z of E F of E dE. So here integration limits. What are the limits means? So what is the lower limit here? EC is the lower limit. What is the upper limit? Infinite. Infinite. So that's why here. So what we are taking this limits is EC to E infinite. EC to E infinite. So this is the total number of electrons. Okay. So that is the intrinsic charge carriers. Okay, okay. Remaining we will discuss about tomorrow. So first read these intrinsic and extrinsic charge carriers. Extrinsic charge carriers. Then you know about the. And so if you will get doubt means you can ask tomorrow. So otherwise you will not get any doubt without reading. Without reading. Okay. So first I will take the attendance. Yes, if you have any doubts means you can ask, otherwise you can leave from the session.